Morning, everybody. So I'm Hans van Winckel. Among other things, I'm also responsible for the Mercator telescope with many others. So today is a team representation or presentation of 15 years of HERMES, which is the high-resolution spectrograph on our telescope. So my talk will be divided in two parts. First is really the operational and what did we learn after 15 years. And the second part is then what are science highlights and what kind of science are we doing with the instrument and what kind of science can we do with an instrument that we own ourselves and we have a personal relation with every screw of the spectrograph. So Mercator is a 1.2 meter telescope for those who are new to our institute. It's a semi-automatic telescope, which is a twin telescope by the Swiss. So we build them together with the Swiss telescope, but since its start, let's say, we diverged quite significantly, and now, except for the hardware, there is little in common with the Swiss. We operated from La Palma, which is probably the best site in Europe for observational astrophysics. Where is La Palma? La Palma is one of the Canary Islands. Why is it a good site? First of all, it's high, it's 2,300 meters. It's an island, so there is not much light around. It's also quite stable, so we are above the inversion layer often. Not always, but often. And there is a special law even in the Canary Islands that reduces the artificial light. So there is quite some impact of the observatory in the whole island, actually. So that is one of the reasons, but also it's a very good site, especially for the good natural seeing that we can have. There are some specific aspects of La Palma which are quite interesting if you're there, and if you're interested in many things as a scientist. So this is Kalima, it's called. It's when sand from the Saharan desert is blown over the islands. You even see the interaction of the mountain on the flow of the dust particles. And when we have that, we have to close the telescope because there's too much sand in the air. And in fact, since the 15 years, it used to be a phenomenon which is only in summer disturbing, but now we have Kalima all over the year almost. And I think Jesus is not here, but he will certainly know or experience dusty days quite often. It's also high in altitude, so it used to be, well, it is a subtropical island, so the airport on La Palma is bilingual, Spanish and German, because German like to hibernate in the summer, well, in winter, in fact, on the island. But of course, if you're at high altitude, sometimes you have some bad weather, and it can be really quite impressive that sometimes when the rain is condensing onto our telescope, it's really coated with a very dense and very hard piece of ice, which is very tough to break through. And it's volcanic. So in 2021, a volcano appeared quite in the south, in a location which was not expected, actually. And it destructed 10,000 houses, but it's also quite impressive if you go there and you like the smell of sulfur, go to the south and you will enjoy your stay there. But it's quite impressive, so it's a really mountain that appeared. The island became bigger, and it was just after COVID, so we had an interesting period, 2021, because just after COVID, the island was struck by that volcano outburst. It was quite long. We closed for the meantime, but it's now still affecting our daily operations, because if you want to do something now on the construction work, well, the whole island is being reconstructed in the south, so it's very hard to get people. But the main question of today is, of course, not the island itself, but astrophysics. And so a good question is, why do we need Mercator? Because the big telescopes mean that we are now close to the area of very large telescopes. And on the left, you see the ELT mirror, which is 39 meters. And Mercator is smaller. That translates into, of course, less photons per instrument. And now I have a question for you. You're an observational astrophysicist, and you want to observe Riegel. Riegel is about 0 magnitude. So the question is, how many photons do you get per square centimeter per second, per angstrom? Do you have an idea? You don't need to know a lot of numbers, but this is a number which is useful because it scales. Then you can scale. Whenever you know that number, you can scale to whatever. So you have a telescope of square centimeter, you point it to Riegel. How many photons per angstrom do you get? Any guess? 1,000. Who says more? Who says less? You know the slides because it's indeed 1,000. So that means that's a 0 magnitude star. A 10 magnitude star, you have 1 photon per square centimeter per angstrom. So that means if you want to have a high resolution spectrograph, you need not only 1 angstrom, you need to pin it into much more finer wavelength bins. You have to build a larger telescope than 1 square centimeter, or you have to integrate longer. And so a typical, let's say, power that we measure from stars is about 1 milliwatt per square kilometer of stars that we see during the night. So your solar panels won't work during the night, but that is the level of number of photons that we have to care about. So it's not by accident that we are building big telescopes because we want to go fainter and fainter. But it's a good number to remember, 1,000 per, so 0 magnitude, so you can scale then per centimeter and or square centimeter and per angstrom. So Mercator is of course limited in 1.2 meter. So in order to be competitive with large telescopes, you have to really find a niche in which you want to excel, because that is what we think is important for, let's say, a stellar type of research is time series. We can do time series, and I'll give you a few examples later, where nobody else can have access to. And that is a strength of our observatory. What is needed? You need good instruments, of course. You need an operational model that allows you to scale all whatever time series that you need. You need observers, you are needed. And we need a very user-friendly, because you want to observe, so we need it to be very user-friendly, and you have to limit the access of observers to the precious instruments. And we do have a continuous monitoring, well, we do have a continuous improvement of our technology, so we are always state-of-the-art, I think. And I think that works quite well. So if you want to have a spectrograph, what do you care about? Is the image of, so this is, let's say, the general layout of any spectrograph, is you have a slit. This is a telescope, it has a certain beam, it has a certain focal length, and the image of this slit to the CCD, which is on the other side, determines what kind of instrument you build. And so you have the width here is a number of, where you link micron at your focal plane to an angle on the sky, and that depends on the focal length and the diameter of the telescope. You image that, typically you go to a collimator, whatever happens in the collimator, that is the parallel beam, you do whatever you want, but then it is reflected back onto a CCD with a certain focal length of your camera. So those numbers are used, are needed in order to build a spectrograph or any other instrument that you're worrying about. So in our design, let's say, of a spectrograph, we have a 1.2 meter, so the diameter of our telescope is fixed. The collimator length you can play, and the bigger the beam, typically, so the beam is the beam of your instrument, one in the parallel beam. If it is big, then it's good for your resolution, your spectral resolution, but everything big means a lot of optical elements, and big optical elements are very expensive. So it relates to the available funds that you have. Then you do the dispersion typically with a grating, and then you have a camera which will bring all the light into the detector. So for a high spectral resolution, for a high spectral resolution, the smaller the telescope, the better. The smaller slit, the better, but of course a small slit prevents a lot of light entering your instrument, so that's no good for if you want to foster every photon that you detect. And a large beam is also advantageous. It gives you an advantage to get to your high resolution. Large beam helps, or large telescope, of course, gives you a better flux. And a wide slit also helps, but it's reducing the resolution. So it's an interplay between what you can afford in beam size and the slit width. So in order, we don't do a slit, we don't use a slit, because it would prevent us to enter, because we need a narrow slit, and if you have a narrow slit, then a lot of light will be lost because it will not enter the slit if you have a seeing of 1 arc second or so. And your slit is a half an arc second, then you lose a lot of light. So we do it with a fiber of 2.5 arc seconds, so we allow a lot of light entering the spectrograph, but then we mimic a slit by, it's called a slicer. And a slicer is at the focal plane of our collimator. We cut the beam into two. It's an internal reflection of a prism that gives you a narrow slit, or it mimics a narrow slit into the focal plane of your collimator. So that allows us to have an efficient spectrograph, because we allow 2.5 arc seconds in the sky, but still have a narrow slit to simulate a high resolution, or to bring a high resolution. The drawback is that we spread the light over many pixels. But so, if you were to visit, or if you have heard the PhD defense of Jake, you will remember a similar spectrograph, which is Marvel, but Hermes is quite similar. So we enter with the light, the collimator, the diffraction grating, we fold beam a few times because of space, and then we do the cross dispersion. All the spectral orders will on top of each other. We have the camera that images everything on a CCD. The design was a PhD of Gert, actually. The design of Hermes. The design of Marvel was, in fact, the PhD of Jake. We built it in a few years, so that's the time frame in which it took to get us the money first. It's about €1 million to build the spectrograph. It was 900,000 was the budget, and we did it with a consortium of people. So science started in 2009. In June 2009, we had the first spectrum. This is a PR slide of the PhD thesis for Gert, so I will bring you to the numbers. This is the other spectrographs. This is the diameter of the telescope on which they are mounted. This is the resolution, the coverage, the flux. The flux per square meter is, of course, the ones that are, because you want to compare the different spectrographs mounted on different telescopes, so you reduce this to square meter. You multiply by the resolution, and then the higher the number, the better, and you make it such that your spectrograph is the best. So, no, it is not, I'm joking, but if you look at the history of spectrographs, I think Pharos was really a quantum jump in efficiency, because it used to be only a few percent. Cut the spectrographs that when I started and I used a spectrograph, the efficiency of the spectrograph, that means the photons on the telescope versus the photons detected, was 2%, 3%. Pharos was really 20%. That was really a quantum jump in efficiency, and many of the spectrographs beyond Pharos copied, in fact, the design. And we did the same, but technology evolves, the fibers become better, and the efficiency increases quite significantly. So that helped us, in fact, so the previous history helped us, in fact, to design a spectrograph which is worth using. We do a lot of software, and that is the PhD of Wim Pessimir did a lot of software, well, the other WIM as well, but the software development helped us to make the whole instrument quite user-friendly. And so this is the layout of the spectrograph. There is not a lot of moving parts. And so the good thing of a spectrograph is you're quite independent of, you're of course dependent of the weather, but the spectrograph itself is quite stable, so you can build up photons as long as you have received photons. So another advantage is you need a pipeline, and the advantage of high-resolution spectroscopy is once you went through coding the pipeline, you can use the pipeline for a long time because there is not much changing. While in photometry, like you do imaging, then you're very much dependent on the seeing and the PSF. For the spectrograph is much less so. Your signal to noise will change, but the stability of the stability of the whole software development from raw data to science-graded spectrum is quite stable. And that helps, in fact, to build. So once we've built it once, and since then we do not really care too much about it anymore. I have to, if I were to change the pipeline now, I really have to think, shit, how did I do that again? Or how was it done? So we do an easy inclusion of targets. We have, for every observer, he writes or she writes a night report, and we read it in the morning, so that whenever there is something happening, we have direct feedback and direct action. Continuous technical developments. If you were to visit, if you do a time travel and you visit the telescope 15 years ago and you do it now, there is quite a lot of changes throughout the operational period of HERMES. The biggest change was certainly the telescope control system. That changed from something which was obsolete or based on obsolete electronics to a modern one. And that is also a PhD from Wim. And he designed a TCS, which is in fact the basis of many of our control systems now in almost all our instruments, I think. And that helped us to, first of all, make it as a research project. That means we really went to the state of the art and to design a control which we can, it's also modular, so we build up new instrumentation onto the thing. So if you are interested, go to PhD of Wim to get to know our thesis. What else? So in 2018, we had a new fiber link. We went on remote observing in 2020 because of COVID. And then we may install a new wavelength calibration unit. But that depends a bit if whether we will deploy it in HERMES or whether we directly go to Marvel. Science exploitation. So that is, let's say, what did we learn? So we do still the 10 nights, so 10 nights a run. So a run is 10 nights or 12 nights. The observer goes there, receives instructions on which programs to observe. All the programs, the PIs are responsible for the information of the programs, and the observer will fill the night, and the telescope goes quite automatically throughout to that system. Now, if you overlook the whole data set, this is the radial velocity standards that we measure over the 15 years, so all the radial velocity measures that we did, and you distribute what is the accuracy that we have, let's say, a stability of about 60 meters per second over the 15 years. It's not as good as many other spectrographs that are focusing on exoplanet research, because our telescope is not in vacuum, so that we have the atmospheric pressure. But that gives you, for many astrophysical applications, this is very good for a for many astrophysical observations like chemical abundances, velocities of binaries, and so on. This is a very good stability. This is an interesting plot. This gives you the efficiency of the spectrograph as measured by standard stars. So this is the date, and this is, so that we have several standard stars. I reduce it to 0 seconds, so to 0 magnitude on a 1 second. And the blue line is our exposure time calculator as given to whenever you want to observe something, you give to the exposure time calculator, and that gives you a number. You see a huge variety, much larger than I would anticipate. You see also so here, so all the peaks there is when we washed or re-illuminized the mirror, because a lot of dust on the mirror prevents us to attain very high efficiency. This period was a dark one, because we had a lot of Kalima then. We wanted to re-illuminize, or to wash, in fact, but then some of our colleagues broke his leg, and we didn't manage to, in that, so it took a bit longer. I don't understand this period, actually, because it's in the middle of the dark period, there is a very efficient, so I have to check that. Here, this is when we re-illuminized, but you see our observers, because we have a photo, we have exposure meter. So during exposure, you know, as an observer quite well, what is the signal to noise of your instrument. Because when you read out a CCD, you remove, so it's a destructive readout. So you have to read it, and then you know what kind of signal you have. But we have an exposure time meter, so we measure, in fact, the light entering our spectrograph. And you see, we have very stubborn observers that really continue till the last photon, because you are in a, well, this is 50, so even when it's almost completely clouded, we still continue observing standard stars. Which is fine, which is very good, but sometimes you can say as an observer, sorry, but this is it's no worth continuing. On the other hand, an exposure time meter is indispensable, because even at a good site of Mercator, like Mercator, the variety of seeing of small dust particles or Kalima is such that there is a huge variety on transparency. And it's not even peaked, so there is a whole range of better nights and good nights. We did lower, so it's not the top efficiency is, let's say, something like 20%, including the telescope. But the instrument itself is about 30%. So we lose a lot of light by just the reflection of M1, M2, and the fiber coupling. But you see, one of them, let's say, on ground-based observations, you really need an exposure meter, because even on a good site, the variety of transparency of the night is very large. And we have to wash regularly the mirror with baby shampoo even. So we do it with baby shampoo, because that's very soft. Typically, we do it once a year. We wash. Aluminization is expensive, so we don't do that that often. In I or in R, I think it's much better. So the R transparency is much less sensitive. In V, it's much more, and in U, it's even worse. So on the science part, so this was the part on the Mercator itself, and what is the quality of our data and our data gathering. Science-wise, so I checked yesterday the number of science spectra, so it's about 150,000 spectra. We have about 500 publications, and don't worry, I will not review them all. We have also a leverage towards students. Now the students are there for their observing school, because they have to write a proposal, and the best ones will go to La Palma to observe. And we have some outreach and educational program. But I'll focus on the science now. And it's interesting to see where do we point. You see the galactic plane projected, but you also see very clearly where Kepler had its field of use. So even you see the individual CCDs on the sky where Kepler was pointing. So needless to say that the combination Hermes and Kepler was and is still a very strongly demanded array space in our observational program. The science and leverage, so we have few data releases. We will release our archive this year, hopefully. But we also have a larger release of very high quality data. Melchior it's called, Pierre was PI on that. And it adds more complexity to the data reduction pipeline because we remove the tellurics and we remove, and we normalize all the spectra and so on. So it's good if you're interested to go to Raskin 2011 paper, go to all the citations. It's about 470 publications, and to have a read through all the titles only, just to have you an idea about what can you do with high-resolution spectroscopy and what is being done. And of course, it's chemical observations, chemical tagging in this case of moving groups, that these are groups that, well, often it's a Gaia release that we have streams and moving groups that are objects that are probably coming from the same cluster that is evaporating into the its project. No, it's a projection onto into the Milky Way, and so we have chemical tagging, and it's amazing because such groups, they are very wide and it's not at all localized in the sky. It's a very huge domain which they cover often. It's really hours of array space that you cover, so you need to observe a lot of objects with a certain kinematic properties. We have tuba or not tuba. That is all the enrichment in barium star of barium, so really chemical composition of a high-resolution spectrograph, of course. We use also a lot of data is in comparison or is in complementary with space, and this is C60+. It's an infrared spectrograph you need to detect C60+, but you can use, you need a high-resolution spectrograph for the study of the star itself. Seismology, well, we are in IvS at the end of the day, so we do a lot of seismology research, which is also often based on space data, where we do then the high-resolution spectroscope follow-up. And here we combine binarity and pulsation and so on. I will not go into, but I do want to highlight a theme in which I think Hermes has contributed quite a lot, and that is all related to binary physics. And here is a very interesting review. I suggest you to read it at some point. If you're interested in binary stars, and you all should, because you're in IvS, this is a cartoon on how binaries evolve depending on the initial mass, the initial separation, and what all different interaction channels go through. Now, many of those arrows, the yellow arrows, are quite uncertain. So there is a lot of uncertainty when a single star evolves into a binary. And it's really, really, I think, observationally driven still, because there is a lot of uncertainty in all the aspects of many of those systems. So a lot of us are working on the high side, high mass side. That's Hughes group and all, well, many of you. Some also are working on the lower mass side, which is different because the end product is not a black hole or a neutron star, but a white dwarf. You have some supernova type 1a, you have some supernova type 2, and depending on the initial construction of that binary, whether it's a wide binary, a short period binary, an eccentric binary, you will evolve quite differently. And so many of ours, if you were to count all the papers that we published in binary star research, it's quite a lot. Another thing is, for massive stars, they dominate the population, so there's a lot of binaries in massive stars. For solar-type stars, it's probably like around 0.5%. So 50% of the solar-type stars are probably in binaries. Not all will impact, well, the evolution of not all of those objects will be impacted by binary, depending on the initial orbit, but still a lot And so why is it so complicated? I think it's complicated in many ways. And here I depicted a few of the physical mechanisms which are important if you worry about binary evolution. First, the tides. The tidal interaction is not very well understood, and I'll show you a few examples later where it's clearly the tides did not circularize the orbit at the rate at which we think they should. Then wind interaction, when the star is still white, but the wind can be deflected. There is also, it can impact also on the dust properties or the dust creation process throughout this. So that means that even white systems can have a different evolution depending on how the mass loss will evolve by binary interaction channel. Whenever you have a Roche slope overflow, and in low mass stars, that often happens when the star becomes a giant, convective, and when you remove mass from a convective star, you become larger. You don't shrink, you become larger. And that's the biggest difference between more massive stars and low mass stars is whenever a solar type star that will increase its radius by 215. You go from a 1 solar to an 1 AU, that is 215 solar radii. So you have an increase, an immense increase in convective, and you become completely convective, and that impacts quite strongly how you interact. So if in a convective star you do the Roche slope overflow, that often it's a catastrophic event. You cannot cope with all the mass, and you go to a common envelope. In a common envelope, you will shrink because you remove orbital energy to thermal energy to remove the envelope. And typically, those orbits will be smaller. And there are many examples in many of the planetary nebula central stars are spiraled-in systems. You have CVs, which are a white dwarf in a closed orbit with a main sequence star. All those systems are produced by that common envelope channel, which is by itself quite difficult to model, and there's quite some uncertainties on how to model that. And it's also here, it is quite observationally driven. So if you look at the binary distribution that we start off, and this is a solar type binaries, this is period in days. So this is the main sequence binary population to start with. Any population synthesis model will start with kind of distribution of the number of binaries at a certain angle. The Roche slope and common envelope is from, let's say, 1,000 days, typically. If this binary is 1,000 days, they will interact when the star swells to its giant dimension, and it will shrink. The wind interaction, that typically widens the binary, and those binaries will be longer, but then we are talking about 10 to the 4 days. So if you do then the calculation, it's a population synthesis, you end up with a distribution of and there is a peak around short periods, which is the product of that common envelope evolution. Then there is a peak of a wide systems, and in between there is not much. There is, or at least you expect not a lot of systems to end up in that regime. This is a different representation because here I've put eccentricity as well. So the darker the blue, the more objects you expect. But I've done it such that I include now eccentricity in that distribution because that will give you some indication. So we do with Mercator a lot of observations. We have a whole system of following up. And these are, let's say, the longer periods. And you see, this is, I've put 0 to the first measurement. So 4,000 days, this is it's a very nice eccentric orbit. This is very interesting if you want to study it, because at a few days, it's a long period, 5,000 days or so, but the eccentricity makes that it's a huge eccentricity in order to explain this one. This is another example for a very long period. And this is, in fact, the longest, there's a planetary nebula with the longest orbital period that is about 3,000 days. So we have the capacity to follow all those binaries for a long time scale that gives you a good measure on the population at the end. So we did that for many systems. We observed them regularly. So all of you that went observing one of those points is probably from you. So thanks a lot. And what do we get? if we follow the whole population, we measure this one. So right in the middle, which is least predicted by our understanding of binary evolution, we measure most systems. On top of that, they are eccentric, much more eccentric than you would expect from, because the tidal forces are very strong when you're close to a Rose-Lobe overflow. Or when the star is deformed, the tides are expected to be circularized very fast. So it clearly doesn't happen. And this is the post-CDB sample. So this is, let's say, solid-type stars at the end of their evolution. But it's a common property. It's a common property also for white dwarf binaries. This is the white dwarf binaries. So also there, of course, here we are not. We have a few objects with our 10 to, because 10 to the 4, that's a lot. That's a long time. That's even more than the Hermes lifetime now. So here we are not completely complete. We are not completely complete. In fact, we are very far from complete. But here we are quite well establishing the whole distribution. So there is a lot of interesting questions because we can observe for such a long time and we have a good indication of the distribution of all those orbits. So this is a Barum stars. This is, well, CH star, eccentric S stars. These are all binaries polluted by the white dwarf. So these are all post, well, some of the, one component is a white dwarf. It's an old white dwarf, you don't see it, but the orbit is observable thanks to the radial velocity measurements of the companion. And we have also SDBs, which are also evolving from the red giants branch. They're, as they expel their envelope, they just expel their envelope when the helium core burning starts. So that's an SDB star. And also these are much more eccentric than predicted. And so well, there are still many questions, but thanks to, let's say, our long-term monitoring, we can really pinpoint to, first of all, the different populations have very similar properties, and we are still working on how can we explain all those orbital properties, much more than just an individual object. So what else do we do? And I have to check the time. So what we can do is study also not only the orbits, but also how do lines change when the star moves in its orbit. So this is in velocity space, and we show every spectrum twice. So we do 2 times the cycle. And so one cut through this representation is one spectrum. We do also interpolate between the different spectra of different orbital phases to make that a fluent, interpretable dynamic spectrum. So this is a moving star, so it's a binary which has a certain period. We fold it onto the period. We see at many objects, we see an absorption component when the companion is in front, and that it's always when the companion is in front, we see an absorption component, in this time in H alpha, that is quite high velocity, 400 kilometers per second, 300 kilometers per second, and it only appears when the companion is in front, so when there is a jet, so there is an outflow generated by the companion that comes into the line of sight through the star, which is the main star, and you see that absorption component. Olivier knows many of those details as well. So you can only do that because of the time series, of course. You have to have a good idea about the time series, and you can use that because you can use the time frame in order to see at which moment is which part of the light covered by the jet. So we do a tomography of the jet by looking at the time frame difference, or the time difference of your continuum light, which is provided by the background star. There is some emission, the origin of which we don't know very well, but we see it a lot. We see it in almost all of those interacting binaries. So this is an example. Sometimes we look quite pole-on. If you look pole-on, I'll go back, then you're always looking through part of the jet, and then you see the absorption component in the blue, always. You see there is a variety of morphologies, and that means that, in fact, what we observe is really an interacting system. They are now still in interaction phase, and we think that it's the circumbinary disk that provides the material, which is then accreted and then blown off in a jet. But there is still yet a lot to be studied in order to really understand the physics of it. We can model it by geometry quite well by imposing a certain geometry on the jet, a certain angle, dependency on the velocity and density. That works quite well, but of course we have to understand why, what is the physics of this emission of that companion. So let's say the message here is keep on observing interacting binaries, because there is always something very interesting into the physics. Other objects that are interesting for long term is we have giants with planets, but also giants with planets, and we have a very long time trend which we don't understand yet. So we have quite a few of those where there is a planet around the giant, but on top of that there is an even longer time frame of change of the mean radial velocity, and the origin of which we don't know yet. Another program deals with eclipsing binaries, and many of you will probably know this program by its number. It's, I think, 121 is the number of program. And that is, whenever you have eclipsing binaries, you measure the phase result spectroscopy. That gives you much more information about the really physics. And then we are working, I think it's Andrew is working on that to map or understand the eclipsing binaries with a short period. Also there, our added value of having HERMES is that we can do not only one, but we can have hundreds of those too. Well, 100 is maybe exaggerated. I don't know how big the sample is, but it is quite large actually. It's a few hundred actually. Massive stars. Massive stars also there. There is a lot of interest in binary interaction physics with not only the whole sample, but also the product of interaction. So we study quite intensively the post-interaction products to understand, well, black holes, of course, whether black holes are present in non-X-ray binary systems. And often we are on the bad side in the sense that claims in the literature turned out not to be the case. So we have de-discovered, how do you say that? If a discovered black hole is found to be non-correct, how would you say that? It's a de-discovery, no. Anyway, and that is the agile environment. We have an own telescope. Whenever such a publication appears, we observe it the next day, and we discover that it's not a black hole. And that Huuk is doing very efficiently, and he has a number of papers on non-black hole detections or false black hole detections. Other products of massive stars are also related to BE stars. So BE stars are very fast rotating stars where there is an excretion disk around it, and it's very unclear whether that fast rotation is by binarity or not, and how that is induced. That is also a big program in our time series. So one of the themes of the massive star, but I have to look at the time, is the single degenerate massive binaries. That means we try to find non-interacting binary stars with a black hole, in which the black hole is not accreting. So it's not an X-ray source. And that you need time series, of course, but also it's often disguised with a component which is not very luminous. And so the discovery of a non-luminous star versus a black hole, which is obviously not very bright in electromagnetic waves, is an issue which we are very good at. So honeybees is the program for BE stars and OE stars to look at the binary properties and which binary properties that we can discuss. This is led by Huuk's group, I think, and hunt for massive single degenerate binaries. This is an example. There was a a claim of a 60 solar mass black hole in a system. We observed it the next day when that claim came out, and we said it was, well, we discovered that it was not the case. I think Michael now has, he has a position now in La Laguna. I think he has now Ramona Cajal to keep on working in this environment where he will study massive star interaction. So I'll skip through those slides a bit more. So the message here is having time series helps you to discover a lot of interesting physics, and the method that we use for Mercator is that we have a whole series of those programs. We can ask the PI which kind of sampling do you need, and we try to provide this sampling such that the physics can be studied at the right time frame. We used to do it semester-wise, but we have decided to engage in a few large programs. So with a few large programs, we mean really a significant amount of telescope time will be devoted to a specific science question. One is seismology, of course. It is related to Plato and CubeSpec, and the 16th of December 2026, both will be launched. No, in 2026, both will be launched, so it's not that far from now. Fundamental parameters is also linked to the Gaia DR4, is probably also will provide us a lot of interesting sources that we need high resolution spectroscopy for. And the binary star corundum, there is a lot of binary questions, and I'm sure that the binary question science will outlast the Hermes, but at least I think in that regime we certainly have a certain, we certainly provide quite some insights thanks to our program. Marvel is the next thing, and there we bridge to not only stellar physics, but also exoplanet science, and that's a whole new talk, so I won't do that, but we will keep you posted, and if you go observing, which you all should, you will see it growing as we speak, because we are now in a process of installing the instrument. So what did we learn 50 years of Mercator, of Hermes in fact? So it provides interesting science, and I hope that I convinced you that we do interesting science. Otherwise, well, it's you that do the science. You have a good instrument, you need a good instrument, you need something to optimize an operational model. We need dedicated staff, of course. We need a good technical team. And it's a very complementary thing to all other observational astrophysics, be it in space or at ESO. So we are really trying not to do everything, but we try to be good at what we think we should be doing. And there are many puzzles to solve. We are certainly not devoid of ideas. This is the whole team. We have 2 people on site. Jesus, who visits us today, or this week, in fact, Saskia, and all the rest is depicted here by picture. We need you because we need observers, and as you may have noticed, the last years it became more and more difficult to find those observers. So there are still a few runs which are without an observer, so please subscribe to it. We provide the needed information to operate. There have been a generation of PhD students before you who did operate Mercator, so you don't have to be afraid. And we will take care of all the questions that you have. And if you have questions now, you are welcome to ask them. Thank you.
Well, thank you for the interesting talk. I was wondering, we had this 15 plus years of Hermes. Are there any big improvement plans for the future?
So we are bothering now with Marvel. So Marvel is our, let's say, priority. Within Mercator, I think the original plan was to devise a wavelength calibration system based on a Fabry-Perot étalon for Marvel, and we wanted to do it on HERMES as well, as a test, as a technology tracer or enabler, let's say. But time-wise, we probably do first Marvel and maybe HERMES later. So that will be the biggest improvement. I think we will not do it in vacuum, because that is the 60 meters per second that we have now. For many astrophysical questions, that is more than good enough. What we do improve also with the Fabry-Perot is the inter-order calibration, because we have a much denser and equal set of lines to calibrate very well every order and the whole spectrum. Because now we see some variation in different spectral orders because of the calibration, and with the Fabry-Perot you can do that much better. So it will not mean a very big improvement in a sense, but it will enable us a bit better to do the wavelength calibration itself. But it will not improve by a huge number. No.
Other questions?
Thanks, Hans. I was really intrigued by the circumbinary jets that you showed. Can you go back to the slides and can you tell us a little more about the systems? Like, is it you really observe it for stars of every mass? Is there any specific how to say it? Are there any specific properties of the binaries that exhibit this, or is it every interacting binary?
Thanks for the question. Of course, it's an interesting subject. So what we did to find them in the first place is we looked at evolved stars, post-AB star or post-RGB stars, that have dust near to it. So the near-infrared excess is a token for something hot dust in the system. And it turned out to be a disk. When we look at the interferometry, we do CO, we see the Keplerian kinematics. All the systems have very strange periods with strange eccentricities, and they almost all have a very special chemical composition on the surface because the star connects to the circumbinary disk and accretes only gas and not the dust. And that tells us that because the gas has a different chemical composition than dust, you will make your star chemically peculiar. So that was the first indication that there was an interaction between the circumbinary disk and the star. And then, in fact, we always were puzzled by the H-alpha until at some Blue Monday, we decided to phase it, and we said, oh, it is related to the orbit. And that brought us to those jet formation. And it turns out that it's very common. In fact, very many of those objects have kind of interaction indicating that there is an accretion disk. And whenever you have an accretion disk, depends a bit on the property of the star that we don't see. We don't see the main sequence companion because it's too dim compared to the post-AB star, which is a few thousand solar luminosities, but we do see that jet. And it's quite common. And now we are studying what kind of mass is involved, and we come to an uncomfortably large number, so 10 to the minus 4 solar mass per year. And that is a bit too high for which we can account for, knowing that all those systems do have those jets, and knowing that the total mass of that circumbinary disk is only a few hundred solar mass. So we have an issue with it's not very clear whether we are wrong in our mass estimates or mass loss estimates from the jet, or that we are right, and then it should be a very transient phenomena. But we see it a lot, so that is contradicting to each other. And so, yes, it's very common. We also think that there is a resonance effect from the disk to the binary to pump up the eccentricity. That is possible, provided that the disk lives long enough. And our current way of thinking is that the whole eccentricity problem, also for white dwarfs, comes from the same mechanism, that all those white dwarfs also were at some point surrounded by a disk. The creation process of the disk is not very well known. So we assume that it's created because of L2, that mass is emitted in L2, but still you have to stabilize it, you have to make dust, so it's not at all trivial to make such a disk. So the current understanding of the disk formation process is very scarce, is very, very poor. So there's still a lot to understand of those systems.
But given how common it is, I mean, there should be some way, and
Yes.
the lines along which I'm thinking is
Yes.
more in terms of population modeling
Yes.
of low mass binary systems, so
Yeah.
white dwarf binaries and also like other binaries. And I don't think we account for
No.
something like this in population synthesis
No.
models at all.
No.
So yeah, this is
That's
something very interesting. And if accretion rates are high enough, yes, it is, yeah, we should really include this. This is very
Yes.
interesting, and yeah,
Yeah.
thank you.
I agree.
maybe, yeah, if, maybe somebody
we
will have
can
to write
talk
a
later.
proposal and actually add it to codes.
Yes.
It will be something really cool to see.
Yeah. Well,
Last question.
Thanks, Hans. Really interesting talk. I'm asking this question out of curiosity.
yes.
So
It's
are
good
there
to ask questions out of curiosity.
so are there plans for installing HERMES or another duplication of HERMES on a larger telescope as visitors instrument, which will give the probing capability a more deeper? So are there any plans for that?
No.
Yeah, just
Well, so the international observatories have much bigger telescopes, also spectrographs, but the strength here is that it's still doable as an institute of ours, although we are on the limit there because we have now facing problems in populating the number of observers. But if you want to do the same just on a larger telescope, you need much more money because, I mean, it's not linear. The price of the telescope is not linear with the diameter. It's quite exponential. A night of the ELT, to give you an idea, one night on the ELT is 1 year of HERMES. So one night is 300,000 euros for the ELT. And we run typically 1 year with this. So yeah, you can't scale it up that easily.
thank you.
Okay, let's thank Hans again for the nice seminar.
Thank you.
And next week, I think it's Reinhold who's giving a talk. So see you next week.